Hello. In this video, I'm going to present to you me and my colleagues' work, ETHBMC, a bounded model checker for smart contracts. In the year 2008, the global financial crisis happened and undermined trust into the financial sector. So, for example, the infamous Lehman Brothers collapse was September 2008, and in October 2008, just 1 month later, Bitcoin was proposed. In the beginning, Bitcoin was treated as, or basically the main idea is a payment network where participants can send each other money without the need for a trusted third party, i.e. a bank. So given the circumstances, the idea took off, had very much popularity back in the day, and was also very much recognized in the academic and industry space, mostly for its backing technology, the blockchain, which solved multiple technical challenges that had been unsolved this far. To explain to you what smart contracts are, let's take a step back first and look at what the typical cryptocurrency does. So this is basically a network of participants identified by an address, in this case an hexadecimal string, most often a public key, and identified by this, users can send each other money in the network. And the great advancement of smart contract was, or the insight was that, well, if we already have a digital network, why not have more logic in the network itself? And basically, this was proposed by Ethereum, and Ethereum replaces, up to this point, all user-controlled accounts with so-called smart contracts. So a smart contract is a program, essentially, which lives inside of the payment network. And then all participants of the networks can use the smart contracts, can use the smart contract and the logic inside of it. And then you can, inside this logic, encode various events. For example, if event X happens, we send money to Alice. And if the event not happens, we send money to Bob. And this way, you can build very complex systems directly on the blockchain. As all programs do, however, smart contracts contain bugs. Very early on in the development of Ethereum, there was the infamous DAO hack, where back in the day, 50 million worth of currency was stolen. By now, this is probably more worth in the realm of over $1 billion. And then various other hacks happens, for example, parity 1 and 2, albeit parity 2 not being actually a hack, but more of a programming error which froze a lot of funds on the blockchain. But, well, our community has analyzed programs for the last 60 or so years, and we can also use these techniques we have developed for regular programs on the blockchain, or on smart contracts rather. And the technique we choose was symbolic execution, so I'm gonna give a little small introduction. On the right, you see a very simple program. The function takes a number as input. If the number is 1, the program says hello. If the number is 151, it says goodbye. And if the number is 42, well, there's a little bug hidden and the program would crash. And what symbolic execution does, it goes through the program just like a normal execution would. So just like, I don't know, your Java interpreter or whatever would. But instead of using a concrete input, so a concrete number like 1, 3 or whatever, it treats the input as symbolic. So what we do is we go through the program, we arrive at the first if statement, and we say, okay, now we branch. So if the number is 1, we go into the if statement and say hello. Otherwise, we continue. And this way, we try to explore the entire state space of the program, because at every junction, we basically fork execution and explore both paths, right? And we would do this again here. So we have, if the number is 42, we would go into the buggy code. Otherwise, we would again continue and thus explored all the possible state spaces in this program. And what we do then is we have this tree of state space, and we encode this into a logical constraint system. And in this logical constraint system, we can reason about our program. So, for example, you could ask the question, is there a phi for which we reach a bug? And well, we then use a solver for our constraint system and obtain the answer, yes, actually, for 42, we reach that bug. And we are not the first to do this. There's been multiple proposals from the security community and from industry. And we analyzed all of them, and we found them to be lacking at least in one of the 4 categories. I will go into very sparing details here because you can check out the paper for details. But basically, all tools we analyzed lacked in the category of inter-contract reasoning. The Ethereum system rather allows during a contract execution to this contract also execute another contract. So what you can do is basically plug together various contracts and thus get very complex systems. And all prior work lacked proper analysis capabilities for this. Thus, we actually became the first tool to analyze and find the infamous parity bug, which I told you about earlier. Then the program code actually gets executed on a virtual machine, the Ethereum virtual machine, which offers an opcode for, or like a mem copy like opcode, like you might know from C. And this one was not correctly modeled in all previous work. And we leveraged a proposal by Falke et al., which proposed for the C memcopy function, and we adopted it for Ethereum. Then the catch-check function is notoriously hard to model because it's a hash function, and symbolically modeling every possible outcome of the function is impossible, since, well, otherwise it would be a rather bad hash function. And we proposed a new encoding scheme for the catch-check function, which allows you to at least reason more precisely about the possible outcomes of the function. And then finally, we found that a lot of tools actually lack validation. So what happens during program analysis is that you have to use some kind of over-approximation, right? We do a more precise analysis of catch-check, but we still, to some degree, have to over-approximate, because if we could reason about the outcomes of catch-check, we could also break catch-check, right? But what you can do is, once you have your logical encoding, you actually get a valid, concrete output for which you reach a certain statement in the code, or for which you violate a certain property you want to test. So what you can do is you can do an offline simulation, and we found that a lot of the tools actually do not correct for over approximations. And then to basically demonstrate that our tool also works at scale, we did a scan of the entire blockchain. So as of December 2018, we analyzed over 2 million contracts and found 4,300 to be vulnerable, which was more than all previous work. During this analysis, we analyzed around 90% of our contracts successfully, but we only spent 30 minutes per contract, right? We could technically use other solvers or analyze our equation system longer, but we had to impose some kind of timeout. The remaining 10% are also in the most complex contracts in the blockchain, which also contain the most value, right? And probably still like the most interesting out there. And actually, you can analyze most of the contracts on Ethereum are rather simple. Here I plotted for 10,000 samples from our data set how long it took to analyze these contracts. And as you can see, the timescale is not linearly, but in the first 5 seconds, we can already solve half of the data set. And after 2 to 3 minutes, we have analyzed roughly about, I think it's like 85% of the data set. After that, we steadily increase until we reach the 90 and the remaining are timeless. To prove that that we found more contracts, not because of better engineering, but rather because of our techniques, we took a subset of the contracts, and the baseline basically refers to our tool analyzing that subset without our improvements turned on, so memory, catch-up, and the intercontract reasoning calls here. And what we did then is we turned memory on, reanalyzed the data set, and recorded how much bugs we then found. And for each of the improvements, we found we found more bugs. So actually, all of them contribute to the overall number. And note that memory seems rather small here, but we basically have such a precise memory model to enable correct reasoning about catch-up and intercontract reasoning. So, more precise analysis of smart contracts is possible. It does scale to the majority of contracts, but again, most complex contracts still need work. Again, we could only analyze 90%, but hopefully this will get improved on in the future. You can find our code online, and if you have follow-up questions, you can reach me via email or on Twitter. And I hope I piqued your interest and you check out our paper.